So last time we just looked at a few channels, special examples of channels. The last thing I wrote on the board, I think, was the von Neumann measurement channel. There will be lots of more channels that we have to look at in detail and what they can do and so on. So consider this as just a few initial examples. So one thing I wanted to add to this is an explanation of what the corresponding objects would be in a classical theory. Right? So this often helps to get an intuition of what this is all about. So I wanted to make a few remarks about the classical case. So, so the same boxes apply. Right? So any classical probabilistic theory can also be understood in the same terms, namely we are preparing systems in some way, maybe do some transformations, and in the end make a measurement and get some probabilities out, right? So relative frequencies. So we had so the general so the general scheme is exactly the same. So just we have to fill in the details. What are the mathematical objects here? So quantum. We had a positive operator here with x1. The channel is a map between the Heisenberg pictures. This is H out, H in. It goes from H out to P of H in. And T is completely positive and probability preserving, and the observables would be there would be results x in some outcome space, and this corresponds to positive operators that add up to the identity, of course, on the H out space here. Right? So this is the structure that we had set up so far. So classically, this is quite similar. So only instead of the trace class, we have a different space in which the probability, well, these are probability distributions. Let's say on a set X. So for simplicity, for the moment, let's just think of this as a finite set. But this is really only to keep things as simple as possible, so to focus on the conceptual part. So what is that? That is a function on x is to the positive real, so rho of x is positive. And rho of x would be the probability that the source or whatever system, that the preparation gives a system with properties x. So the set x is sort of the list of all possible combinations of properties of our system, and the preparation just produces systems with some properties with a certain probability, and rho of x is the probability to prepare for this particular procedure of preparing to prepare so that out of that process the property combination x comes out. Right? Now these have to be positive and add up to 1. And you see here the analogy exactly, right? So there is a positivity condition and there's a normalization condition. That's exactly as in the quantum case. The x here, actually maybe let's call that the sample space, or yeah, that's sample spaces, common terminology in probability theory. Now, the observables here would be the same things. So we would have functions from x to r. Well, let's say I shouldn't have called that x because there's a possible confusion here between these sets. Right? So let's say for an outcome A, this is an A sample space point is positive, so this is a positive function, and the sum of these is again 1. So it's exactly the same thing. So these are positive functions that add up to 1, so it's also some, if you are familiar with differential geometry, there is a concept called a partition of unity, which is a set of functions that add up to 1 and that you use to cut up your space. Right? Now, what do you get in the middle here? Oh yes, and there's a formula for the probability. Right? Formula for probability. So quantum, so the probability to get the result x, let's say the probability to get x is the trace of rho with this operator. And the classical formula is that you just get the sum, so rho of x, that's the probability of A now. Now, why did I get confused about the sample space X and the outcome space X? Well, there is a particular measurement that we could call the super measurement that just reads out all the properties in the classical case. Right? So, classical case, this is one of the differences. In classical, there is a super measurement. Which just reads out a property combination X. So this super measurement formally actually has index x and is a function, just a delta function. And so for that measurement, the probability here, the outcomes will be just the same. In that case, these are the same. This is why I confused them in the initial way to write this. So these are the same, and we just get the probability out. So, but in general, actually, you don't have to. Many measurements are not that exhaustive, right? So you would just. There's a question there.
What does it say after which just reads out?
The property combination. I said so. So the sample space X gives you a complete list of the possible combinations of properties. That's what I said. So this property is just the readout of the super measurement. Okay. So this is actually one of the differences here. And now in the quantum case, we had a picture of a quantum state space, which was a Bloch sphere or a Bloch ball. So what does this look like? So does somebody have an idea what that looks like? The possible states. So the shape of the state space. So So quantum we had Bloch Hall and generalizations. So this was just, of course, a two-dimensional case. So two-dimensional Hilbert space. And this is in many ways misleading. So if you go to higher dimension, there are many features that you don't understand by analogy from the Bloch sphere. But classically, this is these are the simplices. So I have to explain that. So so the example. The size of the sample space, let's take that to be 3. Then we need numbers, row of 1, row of 2, row of 3. These are positive numbers, and they add up to 1. So let's look at the geometric picture for that. So these are the axes, row of 1, row of 2, row of 3. And now, so every possible state, every probability distribution on 3 points will be represented by a point in this three-dimensional diagram. It will be in the positive octant, right? So the positive sector here, all the components are positive. And the sum is 1. So in order to draw that, we take 1 on each of the axes, and then we will be sitting in a plane that is spanned by these 3 points, in a triangle that is spanned by these 3 points. So the shape of this is the shape of the set of probability distributions on 3 points. Right? Now it's pretty clear what the interpretation of these extreme points is. So the points here on the outside, they correspond to a deterministic preparation, where the source which is produced always the same property combination, and there are 3 possibilities, and they correspond to these 3. Right? Now for x equal 4, we would have a tetrahedron. I guess you can see what I mean, and so on. Now, so I said, so this generalization. So of course, for 2 points, you just have a line between 2 points, and then this is a 2-dimensional simplex, a 3-dimensional simplex, and so on. So the distinguishing feature of a simplex geometrically is that every point in the simplex has a unique representation as a convex combination of extreme points. So we'll get more convex terminology as time goes by. So let's start with what is an extreme point of a. Well, first of all, what is a convex set? The convex set is a set with a property that with any 2 points, also the line connecting the 2 is a member of is contained in the set. Right? So this convex combination has an interpretation, both classically and quantumly. It has the same interpretation, namely randomizing the preparation. So if you have 2 different preparations and you flip a coin deciding on which to use, you still get a legitimate preparation, which will be, if it's a fair coin, it will be 1/2 the sum of the 2 rows, whatever, be it probability distributions or that. In both cases, the same interpretation, and it does the same thing, right? So the convexity is a natural property of state spaces, and the operation of mixing is this statistical operation of randomizing your preparation. And now, an extreme point of a convex set is a set that cannot be properly represented as a mixture. Right? So on the Bloch sphere, every point in the inside I can decompose into 2 points on the surface, but the surface points I can't decompose in any way. Right? And so those are the surface points are the extreme points, and in this case the extreme points are finitely many. Right? So I have infinitely many extreme points in the quantum case, but only finitely many in the classical case. And the property here is that the weights to represent every state here are actually just the coordinates that we're talking about. Right? And there's a unique way of representing each point as an extreme point of these three. Right? Because if you think of this in terms of linear algebra and the vector here, this is the basis. So there is only one way to represent that as a linear combination of these points, and therefore this is must be the unique representation. So that's the definition, the geometric definition of a simplex. And the line or the succession of simplices with growing number of extreme points is a point, a line, a triangle, a tetrahedron, and so on. Actually, in infinite dimension, you get subtle differences between different infinite dimensional simplices, but that can wait, I think. Okay, so this is the geometry of the state spaces, of the classical state spaces. So there is still this question mark. So channels, there would be an X in and an X out, and and some transformation T. So it has to have the property that Tf, so if F is positive, it must be that Tf is positive, and T of the identity is the identity. The identity in the classical case, of course, is just a function that is constant 1. That's the thing that we use to normalize, and in terms of a measurement, it's the measurement, trivial measurement, that just counts the number of experiments that we've done. Right? So, so what does that mean? In particular, so let's say this is a linear map, and F is just given by, let's call this X, right? And let's call this Y. Right? So the inputs are in a set X, the outputs are in a set Y. Now F is a function on the output space, but this must be a function on the input space. Right? So again, T is now in the Heisenberg picture. Right? So there must be a matrix F of Y, that does this linear operation. Right? Now, F of Y may be the function, may be a delta function. So the super measurement is clearly a possible measurement. And therefore, if I can just pick out a single term, but that is positive, a delta function here is a positive function, and therefore what I get out must be also positive. So the first condition is that T of xy is positive. And the second condition is that if I put the identity there, that is, if I just sum over y, then I put the identity function here, then this must be 1. And this is the sum over y for all x. So a suggestive way to write this is also to write this as, so T of x, y is the transition probability from x to y. So I have an input state in the pure state in the sense of list of properties that describes the input system, that is X. And if I have that, the output will be a probabilistic mixture of different possible outputs, and they occur with this probability Txy. Because this just says if I fix X, I have a probability distribution with respect to Y. Very natural interpretation. Right? So I go in with a well-defined state, and I get a randomized state out, and that is described by this. So channels, in the classical case, are transition probability matrices. Okay, actually, applying, so this is the channel in the Heisenberg picture. What is the channel in the Schrodinger picture? Then I write this as a transformation on state. So Schrodinger picture so I have an input probability distribution, and T star rho is now an output probability distribution, and it's just written like that, right? So it's rho of x, Tx1. It's the same matrix that does that, only that we sort of apply it, so the index that we sum over is the other one, which means it's an adjoint. It's some kind of a transpose. It's used in the same rectangle of coefficients is used in a different way, right? But all the conditions are the same, right? So it's clear that this turns positive rows into positive rows, and the normalization, if rho is a state, that is, it's normalized, its sum is 1, then of course that's also true here, and it's the same condition that does this. Right? So this is sort of a thing to remember, and that is true in the Heisenberg and in the Schrodinger picture. So the quantum case is not much different. You have a few more indices, but the basic story is exactly the same. Okay, so one more aspect, so composition. So I have this so I have two kinds of systems, and they're described by property lists x1, and x2. So what describes them both? A combined system of the two? Well, I just have to give the properties of both systems. So the corresponding combination here, this is in some sense what corresponds to the tensor product of Hilbert spaces, becomes the Cartesian product. But then, I didn't give the notation for these spaces. Of course, I would call this the space of summable sequences would be Lx, L1 of x, right? And this corresponds to the trace class, and the analog of the bounded operators would be L infinity of x. Of course, when x is finite, these are the same space. But I handle them differently, and of course, when x becomes infinite, this does make a difference. And so then actually, L1 of x, so this would be the probability distributions on the Cartesian product are indeed equal to the tensor product So I mentioned that we have tensor products. In the quantum case, we have tensor products at the vector level, at the operator level, and at the superoperator level. Right? Now, in the classical case, the tensor product at the vector level becomes replaced by the Cartesian product, but all the rest is the same. So this actually means that rho 1 tensor rho 2, this is a probability distribution, two independent preparations, one of system 1 and one of system type 2. So this becomes a function of two variables, and that's just a product. Right, so this is just independent preparation of the two possibilities. And, okay, so at the level of states and observables and spaces, linear spaces representing that, was that a half-hour break? No, not yet. Huh? Not quite. Okay, so at the level of these spaces, I do just get the tensor product in the usual way. So this also means that hybrid systems they describe combinations of classical and quantum information. And so they are described in a tensor product of spaces for states and observables. Okay, so we're not going into the hybrid game at the moment, but we might need that at a later stage, and then I'll come back to that and we'll set up the tensor products. By that time, you'll have some more experience in handling tensor products, and this will actually be a useful thing, a useful observation. Right now, it would just be a complicated notation for something simple. Right? So. Okay, what is still said to be still to be said about the classical case? And I don't really want to say it. I mean, I'm not describe it in detail. So, what happens when the set of elementary possibilities, the sample space, becomes infinite? It can become infinite in different ways. For example, it could just be discrete points, discrete possibilities, but infinitely many. So then the possible descriptions of systems would be maybe by integers, and all integers are possible. But it's also possible that the space X becomes a continuum. And this can be handled in different ways. So actually there are 2 points of view here. So we could think of X as X with topology. And X with measure. So the states could be in so observables would be in the continuous function on X, or the states could be in L1 of x with some measure. Enough of break? Okay, I have to practice this. So actually, both points of view are possible. There are different ways of handling the infinite case. So, and I'll come to that when we need it. But just to make clear that taking x as a finite set really is only for the sake of explanation. These infinite cases do appear quite often, and topology and measure theory are basically different ways of handling this infinite situation. Okay, so this is time to erase. Are there questions about this? I'm aware that I didn't really explain this, but just left a hook for later. Okay. Okay, so the next thing I want to talk about is the positive cone. And I'll change from giving rough sketches of explanation to doing things in detail. So now if you don't understand anything in this section, please do ask, because this is very fundamental, very much needed for the whole field. So, let me just describe positivity. And I'll do this in the form of a lemma. So this is the description of what we call positive operators. Positive operators already appeared, and I basically assumed that you know what they are. But now let's go a little bit slower and take that very carefully. Different ways of defining that and seeing how these are related. So there's a lemma here. So we take an operator. It's a bounded operator on a Hilbert space. Hilbert space might be infinite dimensional, right? The following are equivalent, right? And actually actually, this lemma describes the notion of positivity, so let me just mention that first. But this is sort of true by definition, right? A is positive, or in notation A is larger or equal to 0. That's my standard notation for positive operators, right? So actually, some people would say here positive semi-definite to be more explicit. And indeed, sometimes I might also say that in order to distinguish that from other kinds of positivity that exist, for example, positive functions or transition probability matrices are positive in the sense that each entry is positive. But that's not what I mean here. This is positive semi-definite, right? So this is the definition part. Now, there are different ways of defining that. And so the first is that for all vectors, psi, a, psi, so this diagonal expectation value, if you wish, is positive. The second is that A is Hermitian, so A is equal to its adjoint, self-adjoint. And the spectrum of A is a subset of the positive numbers. So in general, when you have a Hermitian element, you know that the spectrum is in the reals, on the real line. I discussed that when we talked about the spectral theorem. But now this is a strengthening, right? So the spectrum consists of positive numbers. And the third property is that there exists another operator, also in of H, such that A can be written as B star B. Okay, so that's the lemma. And so basically each of these lines could work as a definition of positivity. And of course the claim, and I'll prove that, or at least sketch a proof, the claim here is that these definitions are actually define the same notion. And that's what we call positivity. Right? Okay, so let's see. Let's start with number 2. So proof. So let's assume that A has this property, and now we are supposed to find another operator such that A is B star B. We are supposed to find B, right? And so the proof is very simple. Then we apply the functional calculus. Here we take the positive square root. It's a function that is defined only on the positive line, right? So we don't know what the square root, and for this purpose, we don't know what the square root of a negative number is. We don't need to know that. And if you look at the spectral theorem and how the functional calculus was introduced, you actually need this only on the spectrum. And now, our assumption is that this is actually in the positive real line, so we can apply that. And just as a reminder of the functional calculus, the idea is that we represent the given operator as a multiplication operator on some set. And then we take, it will be multiplying with positive numbers. That's exactly what it means that the spectrum is in the positive, on the positive half-axis. So it will be multiplying with positive numbers. Now we build the operator B by taking the square root of these numbers and making a multiplication operator in the same space. Right? So clearly then, B will be the square root of A. Right? In exactly this way. Right? So we transform, we represent the whole space, we choose coordinates if you wish, we make a unitary transformation to a concrete Hilbert space in which A is a multiplication operator. And then we just take the square root of this function. So in the discrete case, when we have matrices, this will mean that we just diagonalize A, and we change all the eigenvalues, which have to be positive, right? That's part of the spectrum. Right? So we change each eigenvalue, we replace each eigenvalue by the square root and leave the eigenfunctions the same, or the eigenprojections the same. And that is our definition of B. And then, just by the properties of the functional calculus, we have that B squared is A, and also, because this is a real function, that B star is equal to B, so indeed A is equal to B star B. Okay? Why did we have the star there? Well, so this actually in this we get a special D with this property in this case, one that is even Hermitian and even positive itself. Actually, the positive square root of a positive operator is uniquely defined. There's only one operator with these properties and be positive. Right? Okay, but now let's go from 3 to 1, let's say. So now we cannot assume that this is of the special case positive square root. We just know that A can be written as B star B, right? And but that means that we have to look at the scalar product for an arbitrary vector. We have to look at this scalar product. But now B star B, this is a bounded operator. We can just use the definition of the adjoint. So this is B psi, which is the norm of B psi squared, which is always positive. Right? That's a basic property of scalar products. Okay, so we have to go from 1 to 3. Right? So there are two parts here. I have to show that this implies that A is actually Hermitian. Right? And how do we do that? So first part, first show A star is equal to A, right? So that positivity implies self-adjointness. Actually, this is a special feature of Hilbert spaces over the complex field. If our yes?
Sorry, we have to show A star is equal to A. Don't we do from...
sorry, we want to go to 2s, I'm sorry. I just wrote the wrong thing, right? So now it becomes a circle, right? 3 to 1 to 2 to 3. Right? Yeah, so we first have to show that positive implies Hermitian. Right? So how do we do that? Let me show you how I think about this. I actually didn't. There may be a shorter way to do that, but take psi alpha psi 1 plus beta psi 2. So I take a linear combination of two vectors. So basically, the trick here is called polarization, and I'll just do a polarization. And so I can write out the scalar product here. So psi A psi is alpha bar phi 1a phi 1 alpha plus alpha bar phi 1a phi 2 beta plus the complex conjugate. Well, of the previous term. No, let me just write it out. Right? So beta bar phi 2 a phi 1 plus alpha times beta bar everything with the 2. So this is actually the scalar product of the vector alpha beta. Then we have a matrix that has, let me say, the entries of this matrix are phi I a phi j, right? And ij is 1 or 2. And we take the scale, the diagonal, we take again the vector alpha beta in C2 and take the scalar product with that. So actually, I turn the given by basically choosing a basis consisting of phi 1 and phi 2, if you wish. I turn this into a statement about 2 by 2 matrices. So, I conclude from so this is supposed to be positive, right? And alpha and beta are arbitrary coefficients. Right? So this means that So this implies that the matrix, call it Mij, phi I a phi j, ij goes from 1 to 2, right? Is positive in the sense of 1, right? So I'm talking about 2 by 2 matrices, and so how do I get the positive 2 by 2 matrices? Yeah, well, but okay, it doesn't actually, I'm going in circles, and I can't really cite what I know about 2 by 2 matrices to you now. So we have to look here. Right? So, so in the, so this is just, consider this as an aside. Right? So, but what I'm basically doing here is reducing to the 2 by 2 matrices, but I'm not making a big fuss out of it. The argument has to come from here. Right? So, so if we look at the terms that are written there, then this is alpha absolute squared, and this is a diagonal scalar product of which we know that it's positive. Right? So this is positive, and this guy is positive. And now the whole thing also has to be positive, but that means that this part has to be real. Right? So the whole thing is a real number. So these terms together have to be real. So so this is again just an aside, and we look at the statement that the two middle terms there together, alpha bar phi 1a phi 2 beta plus alpha, no, beta plus beta bar, which is actually the, yes, beta bar phi 2a, phi 1, alpha. This sum has to be real. And the way this can be real is that the complex conjugate of this guy has to be that guy. Right? Because then I have two terms which are exactly, so this is then, this would then become the complex conjugate of the other one. And we can bring this out by taking alpha and beta equal to 1, let's say. Right? So the sum of these two terms has to be real, which means that phi 1 a phi 2 complex conjugate is the other guy. Right. Okay, so what do we learn from that? Now, the scalar product complex conjugated is just means that on this side I can continue to write this as a phi 2 phi 1. This is a property of the scalar product. If I exchange the two factors, I get the complex conjugate. And now I can apply the definition of the adjoint and then get this one. So sorry, this was the way to do it, right? So for arbitrary, phi 1 and phi 2 were completely arbitrary. So I conclude from this that A has to be A star. Right? Because for arbitrary vectors, this identity holds. So, in particular, so we've shown that A is Hermitian. So in particular, A is normal. That is, A star is equal to A star A, and it follows that A is unitarily equivalent to a multiplication operator. Now, so we can basically do this transformation and consider A directly as a multiplication operator, and we just look at what we learn about this. So all this actually, for the purposes of this proof, would have been completely enough to show that A has to be normal. But actually, Hermitian is easier to show, right? Because now we look at the scalar product in whatever space we are in. So this is just the integral with respect to the measure in the concrete Hilbert space of A of x times psi of x absolute square. So this is a positive integrand. I mean, this is a positive measure, and this is modified by a positive function, and all these expressions have to be positive. So basically, psi of x is an arbitrary, or psi of x absolute square is an arbitrary positive L1 function. Right? And I can make this very sharply concentrated at some point, so I can test out everything about A of x by that. Right? And so this has to be positive for all psi, and this just implies that A of x is positive almost everywhere. And that in turn is just a statement that the spectrum is contained in the positive number. So if you feel happier about discrete things, think of this as think of the special case where A is not just a multiplication operator on an L2 space with continuous measure, but with counting measure. That means that in that case, A has purely discrete spectrum and can be written in terms of eigenvalues. And it's a statement that a positive operator, in that sense, I can just take the scalar product with the eigenfunctions, and if that is positive, then the eigenvalues all have to be positive. Right? So this is a version of the same argument for general including continuous spectrum. Okay, so I guess I call this proof. Are there questions about this proof? There's a bit of black measure theory magic here, but this is necessary because we do want to include the case of continuous spectrum, and continuous spectrum is defined as the set of values that appear with positive measure. Right? So we can't avoid this kind of statement. Okay, so let's look at some consequences. Now in looking at these consequences, you will see that it's extremely useful to have all the three definitions in parallel, to know about all three definitions, because often one will be the best definition to show something, and another one may be the best for another question. Right? So let's look at some natural closure operations. So I claim that if I have two positive operators, their sum is also positive. So which of the definitions should I use to show that? Suppose I gave you the third definition as your basic definition. This would really be a nightmare, right? Because I would have to write A star A plus B star B as C star C, and this is kind of hard. You wouldn't be able to do a simple proof out of that, right? But look at definition one. Well, this is obvious, right? Because the scalar product is linear, right? So use one. So let us prove that if A and B are positive, then and they now could be in different spaces, then A tensor B is positive. Take definition 1, for example. Then it's a nightmare. You don't really see what's going on. So take definition 3. How does this work? So A is, let's say A is X star X, B is Y star Y. So A tensor B is actually equal to X tensor Y star X tensor Y. There you go. By the rules of starring and multiplying tensor product operators that we've discussed, it's clear that this just gives you A tensor B. Right? So this is also positive. Okay, so this is a good example to see that these look kind of similar, but the way to show that, if you get into any trouble with the positivity proof, try the other definitions. Right? Okay, so now, so if A is positive and X from H out to H in, no, H in to H out, sorry, to H out, A is any linear operator, bounded, then x could be between different operators, right? So, okay, which would you use? Which definition? By the way, in this case, if you look at the proof from 3 to 1, this simple line there, you don't even need that B is an operator in the same space. It could also be an operator between different spaces, right? And you see that here. So if I write A as B star B, then you directly see the operator Bx, that is star and multiplied with itself, to make this result. Right? So it's definitely a case of use 3. And this is a very important observation. Actually, this transformation from A to X star AX is the prototype of a completely positive map, and this is what we need for all the channels. So this is a very, very fundamental observation. So when A and B are positive, actually I should have written that as the third item here, because it's also another combination of A and B that turns out to be positive. This implies that the trace of AB is positive. This is important because our definition of states was positive rho, right? And our definition of a detector operator that for a yes-no measurement, an F, would also be positive. Now probabilities had better be positive, right? So this is what we need to argue, that if we have a density operator and a positive operator, trace rho F, or trace whatever, trace rho times a positive operator is positive. That we need that for the positivity of probabilities. Right? So how do we prove that? Any idea? Yeah? Yeah, actually that's pretty good. We use the functional calculus and take square roots, or actually also using 3 basically. Right? So let me put use 3. The product, well, yeah, I think you want to factorize this, right? So then actually this trace here is trace with the same notation here, x star x and y star y. We have x star x, y star y. And then we multiply that to the other side, so we have, this is trace y x star, x, y x. Right? Sorry, my handwriting like that is not very good. So the trace, this trace can be written as something which is itself the trace of a positive operator. Right? Now, AB is not positive. The product of positive operators is not positive. It's not even Hermitian. Unless, actually, when is this Hermitian? A product of 2 Hermitian operators. For that to be Hermitian, if you star that, you reverse the order of factors. So the product of 2 Hermitian operators is Hermitian if and only if they commute, which is the boring case. Right? So actually here, almost never this commutes. Right? Would be unusual. Right? So the first thing is to convert that into the trace of a positive operator. For doing that, I use number 3. And then you're completely right. How do I show that, that this is positive? Well, all the eigenvalues are positive. It's the sum of the eigenvalues that makes it positive. Or if you wish, if that has, this might have, well, actually a positive trace class operator has discrete spectrum. But if you don't know that, you can still use that, because you're using the diagonal matrix elements and sum over the diagonal matrix elements, and these are clearly positive. Right? So by this definition. So it's a combination of either 1 or 2. Right? In this case, it doesn't really matter. So the trace of the product of 2 positive operators is positive. Actually, so this is one conclusion, and also it's also interesting to know when is this 0. so I still assume that both are positive. And so when trace AB is actually 0, I claim that AB is 0. And BA is also 0, actually. So that's just the adjoint of 0. Now, how does that work? I have to argue that if I have an operator of the form x star x, which has 0 trace, that is actually the 0 operator. Right? So the only way an operator can have trace x star x is equal to 0 is that it is actually equal to 0. Now this you could get with a combination of 2, but let's think of this as a sum of positive terms, the trace, namely the diagonal matrix elements of x star x. Now the terms in this sum would be the norm squares of x on a basis vector. Right? So scalar product, basis vector, x star x, basis vector, is just the norm squared of x applied to the basis vector. These things would all have to be 0, because these are positive terms that add up to 0, so each individual term has to be 0. So this means that x applied to any basis vector is 0. But if a bounded operator is 0 on all basis vectors, it's 0 on all the linear combinations, that is, it can only be the 0 operator. Right? So there is one point here that the trace of a positive operator can vanish only if the operator is 0. And then we apply it to this guy, so actually we conclude from this that y, there should be a star here, that y x star is actually 0, but then we can take this guy and multiply it from the right with x and from the left with y star, then it's still 0, so AB is 0. Right? So actually, so this is also a useful statement that if a trace vanishes, an expectation value vanishes, then actually the product of these operators also has to be 0. Now, more consequences. So if P is a projection, that is P is equal to P star P. By the way, that's the way of writing this sneaks in the condition that P is Hermitian, because such an operator is always Hermitian, right? If you star it, you reverse the order of the factors and star each factor, but that turns P into P star in front again. So such an operator is actually, we know it's positive and therefore always Hermitian, right? We just proved it. This is a way to make sure that it's Hermitian, so I can omit the star, and P is equal to P star, P squared, right? And that's the definition of an orthogonal projection. And a projection would be an operator that squares to itself, an idempotent. And if it's also a Hermitian, then it's an orthogonal projection. So when I say projection, I always mean an orthogonal projection, unless otherwise stated. Now, if I have that, and we have these inequalities, so A is bounded by a multiple of P, and lambda is positive. Right? So, well, lambda has to be positive, otherwise this inequality couldn't be right. So lambda would be positive automatically. So if we have this kind of inequality, then it follows that AP is equal to PA is equal to PAP. Well, the last one follows from the first two, right? And the second follows from the first by taking adjoints. So, if an operator is bounded by a multiple of a projection, it commutes with that projection. And actually you can throw in this additional factor P without doing any harm. Did I say that A, this is also equal to A? Okay. So how do we see that? Pull it down just sufficiently. Okay, suppose so. Actually, lambda equal 1 is enough. Right? Lambda clearly has to be positive. If lambda is equal to 0, an operator that is both positive definite and negative definite has to be the 0 operator. Is that clear? Which definition should we use? I guess the best version is 2 in this case, right? Because that would be a Hermitian operator with a property that it's isomorphic to a multiplication operator that multiplies with a function that is both positive and negative, which means it's 0. So it multiplies with a 0 function. This is called the 0 operator. Right? So something that is both positive and negative is necessarily 0, so we can think of, we only have to prove the case lambda is non-zero, and it has to be positive by this outer inequality. So it's strictly positive actually, so we can divide by lambda and applying everything to a over lambda. So that is the explanation for this statement. Without loss of generality, let's take lambda equal 1. So now A is less than P. So we're looking at 1 minus P times A times 1 minus P. And because this is, we call this operator 1 minus Px, we know that this is again a positive operator. Right? But if we make A larger in the operator ordering to go to P, because A is less than P, we see that this is less than or equal to 1 minus P, P, 1 minus P. Now we use the property that P is a projection. So if I just look at this expression, P times 1 minus P is P minus P squared, is P minus P is 0. Right? So this is just a 0 operator. So actually this operator is 0. Now A is positive, and we can write it as B star B. So we have 1 minus P, B star B, 1 minus P is 0. That's what we conclude. But then it follows that this operator is 0. B 1 minus P is 0, but then we can multiply again with B star, and this implies that A 1 minus P is 0. So, but this is just the first equation here. A is equal to AP. Now I take the adjoint of this equation. A is also Hermitian, so I get that A is also equal to PA. That's just the adjoint of the first equation. And if I have these two, that means I can just add a P in at either end without changing anything, and that gives a third equation. Okay. Oh yes, there's one more property that I wanted to mention. It's related to this positivity of traces. So, to this thing. So it gives us version number 4, if you wish, for testing positivity. Right? And so one more consequence is that if A is in B of H, then A is positive if and only if, which means it's sort of number 4 on that list of the lemma, right? That is equivalent to saying that trace row A is positive for all row in the trace class, Now, that is for all states. I mean, I didn't say trace rho is equal to 1, because I could divide out the trace. That doesn't really make a big difference. But that says that all the expectation values with mixed states are also positive. Now, so there are two directions here, and actually we already proved both. Right? So in this direction, take the special case where rho is so proof for that. Take rho equal to psi psi. And then this expectation is just trace rho A is then the trace of psi A. Now I take this operator and move it to the end. So this is actually just equal to that kind of expectation. Was that black magic? Did you understand this step? Now, I gave you a little speech explaining what a ket and a bra is. These are operators from the complex numbers to the Hilbert space, that is the ket, and from the Hilbert space to the complex numbers, that's the bra. Now, the formula that trace AB is equal to trace BA is also true when they map between different spaces. In this case, the complex numbers and the Hilbert space. So I take this operator and move it to the end. Right? So this is A. This is the first operator, this is the second operator. So I exchange their order. Now the operator psi A psi in this logic is an operator from C to C. It's a 1-by-1 matrix. And I take the liberty to identify a 1-by-1 matrix with its entry. And the trace of a 1-by-1 matrix is just this entry. Right? So that's how this arises. I can omit the trace then, after making this change around, because I'm actually computing the trace of a 1-by-1 matrix. And that's sort of just the thing itself. Right? Okay, so that if all these are positive, in particular, it's positive for these operators, meaning that this is definition number 1. Right? So A is positive. In the other direction, we already showed it, that if you have the product of two operators, the trace will be positive. And rho is positive and A positive, therefore this is positive. So this statement is called duality of cones. And I'll say a little bit more about cones and their geometry. I have 10 minutes, right? Okay, so let's start a new subsection. 1, 2, 2 or so. So this duality of cones is one of the geometric properties of cones. So first of all, what is a cone? Right? So a cone in a vector space is, let's say, from the vector space V, right? Is a set C, so it's a subset of the vector space, such that first, if let's say two elements are in the cone, then their sum is also in the cone. And the second condition is if x is in the cone and lambda is a positive scalar, then lambda x is in the cone. Okay? So this is all very intuitive geometrically, right? I have my vector space here in front of me. The origin is about this corner, and the cone has a property when I have any vector here, the whole ray from the origin through that point and out to infinity, which is actually the positive multiples of that vector, right? Lambda equals 0 gives me the origin. That's always in the cone by definition. But then also with every point, the whole ray from the origin through that vector will be in the cone. Okay? Now, often, example, C is the positive cone of a partial vector ordering. So in other words, x in C is just synonymous with saying x is positive. Right? So the set of positive elements, whatever we mean by positivity, will be a cone if this ordering relation has the property that the sum of positive elements is positive. That's what this says. And multiplying by a positive factor doesn't change positivity either. Right? So this is what I call a vector ordering. It's a partial order always, because there may be vectors that are not comparable in this order. So neither x is larger than y, nor y is larger than x. This happens all the time. Right? So typically these vector orderings are partial orders. So there will be many elements that cannot be compared in this ordering. To take an example that we already saw, but maybe not quite in this language, let's take Minkowski space, or as it is in English, Minkowski space. Actually, when I heard this the first time, I was going wild. But actually, everybody in the English-speaking countries says Minkowski. Right? So Hermann, whatever, guy from Munich, Mr. Minkowski. So anyway, take Minkowski space. I can't do this. So take Minkowski space. It's a vector space. If you sort of fix an origin in space-time, then it becomes a nice vector space. And we have a cone in it, namely the positive light, the forward light cone. And the forward light cone has this property, so that x larger than y means causally after. Right? Means that y can influence x. Or an event at y can influence an event at x. Right? You know this. Right? And writing larger or equal means that we include the light cone itself. So light-like connections considered as causal connections. And the ones that are not comparable are space-like situated relative to each other. Okay, so this is this. Actually, we know this cone already because the R4 is, by just choosing coordinates in terms of Pauli matrices, is isomorphic to the space of Hermitian 2x2 matrices. And the positive cone of that is exactly the Minkowski cone. Right? We saw that if we cut the cone with the normalization hyperplane, trace equal to 1, then we just throw away one dimension. We take a cut of this cone at some level. Of course, my hand waving here is in 4 dimensions now. Right? So, and that gives us a Bloch ball. So it's a nice circular cone. Right? This is exactly what Minkowski cone is like. And actually, you can use this to learn interesting stuff about the representation theory of the Poincaré group in terms of 2x2 matrices. So spinor representations of the Poincaré group use this isomorphism all the time. So this is actually not just a superficial piece of knowledge. It actually helps you to do physics of space-time symmetries. So, okay, so these are cones. But there are many different, the geometry of cones now is a little bit similar to the geometry of convex sets. Right? So for example, what are the extreme points of a cone? Well, it can only have one extreme point. Yes, which is the origin. So if you have a cone, if you have a point on the outside of the cone, so on the, do you call this the mantle? Whatever, or the outside of the cone, the surface. Right? This is never an extreme point because you can decompose it into this vector times 1.5 plus this vector combined with equal weights with this vector times 0.5, right? We're just in the middle. So there's always a convex combination in the cone that makes a convex, that represents this vector on the outside as a proper convex combination of different points. So nothing that you might want to call extremal in a cone is actually an extreme point in the technical sense of the definition for convex sets. So there is a specialized notion of extremality. So X and C is on an extremal ray and you might slur this to saying it's extremal in the cone sense, right? It's not in the sense of convex sets. If 0 less than x, then y less than x implies that y is a multiple of x. Well, actually, I took this as synonymous now, right? So, if I have an element, so that if I consider the cone as describing the vector ordering, and I have something between this point and 0, right? So it's in two positive steps. Then actually you have to be on it. You know that the only way to do that is taking a multiple. Lambda, of course, here is necessarily between less than 1. Right? So there is a specialized notion of extremal rays. So what do you think the extremal rays of the cone of positive semi-definite matrices, the cone that we're talking about? What are its extremal rays? Well, they must be positive operators, right? So they have a spectral resolution in terms of, of other things. And so if you have more than one non-zero eigenvector, the operator would be a sum of two different positive terms. Look at the spectral representation. Right? Spectral representation means eigenprojection times eigenvalue. There can only be one such term, because otherwise you've represented it as the sum of two different things. Each of them would be smaller than the operator, but not a multiple, because you've omitted a non-proportional term. Right? So the only way you could have that is that you have only one eigenvalue. Also, it couldn't be a multiple eigenvalue, because if you have a higher dimensional projection, write it as a sum of two projections onto the subspaces of the space. So if your projection projects to a more than one dimensional space, you can write it as a sum of two different projections. Bad, not extreme. So it has to be a one-dimensional projection. Right? So in positive semi-definite cone, right? So the cone that we are talking about, just to distinguish it from a generic positive cone, where I didn't really say what positivity means. X extremal, X on an extreme ray. If and only if X can be written as phi from. So it's proportional to a one-dimensional projection. Because I didn't say what the normalization of phi is, this could also be any multiple of that. Right? So, okay, so this will be, I've just been switched off, I realize. So that was that. Next week, let us talk about next week. I'm not going to touch it, sorry. I tend to touch my own phone. I always need to, but I know this is not mine. So, so next week, I will be away at a workshop in Bielefeld, which means that you will have an exercise section and a lecture by David. Did you bring copies of the exercise sheets?
It's in Schrodinger.
Okay. So Schrodinger already has 2 exercise sheets. One which will be the exercise session, which will be on Thursday, right? On Thursday, we'll have to explain some of the things that are needed on the exercises. Right? I didn't quite manage to cover everything that was intended. Anyway, so you'll have a lecture on Wednesday. No, wait a minute. Tomorrow is actually an exercise section, right?
Yeah, this tutorial session. Yes,
Okay. There will be a tutorial session tomorrow. For that, an exercise sheet to be done in class has been prepared. But basically the idea is that you can ask all your questions. Next week there will be a lecture on Wednesday and a discussion of your handed-in exercises on Thursday, and maybe some more material to practice on. Okay. So see you in 2 weeks.